So as a reminder of the types of energy that we've met before, so there's nothing new and higher from that perspective. Kinetic or movement energy, the relevant formula there, EK is 1/2 mv squared. Remember, all types of energy are scalar quantities, they don't have a direction. If you think about that formula there, if a velocity was positive or negative, you would get the same answer for the energy. It's a good demonstration of that concept with scalars. Often called just potential energy, but the full name really is gravitational potential energy. But even then the symbol kind of reflects that, EP. The other one I'll talk more about in a wee second, work done. And what it does is not a type of energy, but it links energy to force. And in particular, forces cause changes in energy. So work done is all about changes in energy. And the other relevant formula you need, met before, is a reminder that power is energy over time, or it's the energy per second or per unit of time. Remember, you can use formulas to help you with those sorts of definitions. The units of energy, remember, it's joule, and power is the watt. But then the rest of this unit, then talking a wee bit more about work done and just being clear about that idea. So the phrase that's often used is work is done when energy is transferred. And that's a kind of almost a definition of work done. But really I think it's worth teasing out a bit. What are we saying? What we're saying is that work done is the amount of energy transferred in any situation when a force is applied. So for instance, if a car brakes, then it transfers that energy from kinetic energy into heat and sound through friction in the brakes. And that amount of energy transferred, so you're taking energy away from the car at that point, you're transferring energy away, would be the work done. But it could also be that when a car accelerates, you're putting in energy and you would get an increase in kinetic energy, and that could be measured as work done. So e.g. a car accelerates, right, starting kinetic energy, so let's say it's moving along the road but it comes to a motorway, so starting kinetic energy is 150,000 joules. Final kinetic energy is 400,000 joules, and therefore the work done, don't always launch into the formula for work done, oops sorry, I should actually use, that is a much better symbol just to remind you it's a type of energy. The work done in this case, because you're not given a force and a distance, but what you are given is all the energies involved, so you can work out that the energy changed by 250,000 joules. So the work done is 250,000 joules. And the last kind of part from this unit, and basically there's very little knowledge in this unit, it's really all about practice, is the idea of conservation of energy. So conservation of energy means that energy cannot be created or destroyed. But simply transferred between different types. Sorry, squeezing it in down the bottom. And what this means in practice is that the total energy in any system remains the same. Now, before we do a worked example, I'll list other types of energy which you should at least be familiar with. I don't think you need to memorise these. So the main potential one that we're dealing with in a mechanics unit, right, so i.e. to do with motion, is gravitational. But the other potential or stored energies you need to be aware of are nuclear, chemical. Okay, and just to clarify that difference, we'll do more on nuclear later on, but nuclear means literally coming from the nucleus of an atom, whereas chemical interactions are all about how electrons interact with each other. Those of you who do chemistry will know that. So that's the kind of difference between them. And the other one I would call elastic. It is really just a special case of the chemical, because it's to do with how the atoms interact when you stretch, say, an elastic band, and they try and pull each other back in. So it's to do with how the electrons and neighbouring atoms interact. And similar in action, to be honest, we have a lot of energies which are really just different examples of kinetic energy. So sound is moving air molecules, heat is moving atoms as well, although that is also tied into a wee bit with their potential energy. And the one exception to that, sorry, I should have said electric as well, sorry, it's not the exception, moving charges. But the one that's a wee bit different is light, and once again we'll explore that later on in the course as well. So, looking at a couple of worked examples of conservation of energy in practice, we've got the idea of total energy at top equals total energy at bottom. In this case, the type of energy we have at the top is gravitational potential energy. So it's always worthwhile being clear what types of energy, and because we know it's moving, so now our formula has become mgh equals a half mv squared. Now notice in this question you weren't actually given the mass, and the reason for that is because it actually cancels out from both sides, so you can actually do this without the mass. If you did have the mass, you could just plug the numbers into the formulas and so on, but we can still go ahead with that now. So we can say 9.8, and notice it's 3 metres above, so it's a height, and in actual fact that's a red herring. Okay, we don't need that, so you will occasionally have data in questions that you don't need. Half times v squared, so rearranging that, you get v squared equals 2 times 9.8 times 3 is 58.8, and therefore v equals 7.67 metres per second. For question 2, we've still got this idea, total energy at top. That's what conservation of energy means. So what is the type of energy that we've got at the top? Once again, it's EP. But in this question, okay, friction is important. So in the first question it said frictionless. So what we've got in this question is we know that we'll have some kinetic energy at the bottom, but we know that there will have been work done against friction. Okay, now you might have been tempted when you saw this question, first of all, say work done is force times distance, but you notice in the information you've got, you don't actually have that force and distance. Okay, so in that case you've got to be looking at all the energies involved. Can you work them out and use this idea that work done is the energy transferred, in this case the energy transferred by friction into heat and sound. So that's not the only force present. There is gravitational forces which are transferring potential energy into kinetic energy as well, but this question is asking you about the ones against friction. So we can start to plug in formulas now, and the mass does matter. in this case. Okay, so we're given the mass, so that's 1, and the height, okay, 1 metre above horizontal, and we were given the speed. So don't forget the squared. So we can do all our calculations in 9.8, 4.5 plus EW, so EW equals 9.8 minus 4.5, which is 5.3 joules.